Now we are going to look at the relationship between entropy. So that's what we are looking at, the relationship between entropy, heat, and temperature. How are they related? If we go to the previous example of the freezing of ice at high temperature and low temperature, and we are going to relate what we are going to discuss here. Now, when a reaction releases heat to the surrounding, because you are adding heat to the surrounding, you are exciting the particles in the surrounding. The entropy of the surrounding is going to increase. That's what happens. So I can say that the entropy of the change in entropy of surrounding is proportional to the heat of the system, or to the enthalpy of the system. Here I am putting a negative here because the system is losing energy to the surrounding. That's why we have negative delta H system. Or they are doing the opposite activities. Remember, this is not equally designed. This is proportionally designed. So delta S surrounding is proportional to negative delta H system. This tells us when a reaction releases heat to the surrounding, entropy of the surrounding increases. That's what it tells us. That is one situation. The other situation is when a reaction releases heat to the surrounding, but the surrounding is at low temperature. So if your surrounding is at low temperature, the entropy of the surrounding is going to increase a lot. So let's think about that. Think about a situation where maybe a substance is at 0 degrees Celsius, and you add maybe 1,000 kilojoules to that situation. What are you going to see? Because you are adding heat to a substance that is at low temperature, the molecules are really slow at that low temperature. So adding the heat is going to excite the molecules more. So adding the heat at low temperature excites the particles more, because the particles were really slow. So if you add heat, they will say, oh, we are happy, now heat has come, and they will be excited more, and they will move about. That's what it means. But let's suppose that is one situation. Let's look at another situation. Let's suppose water is boiling at 100 degrees Celsius, and the water is boiling, the particles are moving really fast. What happens if you add 1,000 or 1,000 kilojoules of energy to the water that is already speeding up, that is already moving fast? The water will say, I'm already moving fast, I don't need to change more. So what it means, if you are adding heat to a substance that is already at higher temperature, where the particles are already moving fast, the particles are not going to change that much, and the entropy of the particles is not going to change that much. So what does it mean? what it means is the change in entropy of the surrounding really is proportional to 1 over temperature. This means that if you add heat to a substance that is already at higher temperature, the entropy, that is the entropy, changes less. If you add heat to a substance that is at low temperature, the entropy is going to change more. Now, if you combine, this is 1, this is 2. If you combine the two equations, you can say that entropy of the surrounding is proportional to enthalpy, that is the heat of the system, divided by temperature. So this is an important. This is an equation. I'm messing up my writing here. So you can say that entropy of the surrounding is proportional to the enthalpy, or the heat of the system, divided by temperature. In the end, the final equation will be the entropy of surrounding is equal to delta H system divided by T. So that is, if entropy is given in joules per Kelvin and the enthalpy is given in joules and temperature is given in Kelvin, the proportionality constant, the proportionality sign will disappear, and then we just have an equal sign there. So this one is an important equation about entropy. So entropy of the surrounding will be given by the enthalpy of the system, but I mean negative enthalpy of the system divided by the temperature. So this is our general equation about entropy. So entropy is really related to the enthalpy of the system. Now, let's go on and see how we can use this equation. Now, one thing that we said about entropy, we have said that the entropy of the surrounding, so delta S surrounding, is equal to negative delta S system divided by temperature. So that is our important equation. But we also know that from our previous discussion, we know that delta S of the universe is equal to delta S of the system and delta S of the surrounding. Now, but we know that this surrounding here is here. So we can replace this one by this. So if I want to do that, I will say delta S of the universe is equal to negative delta H of the system divided by T. Now I have just took the surrounding off and replaced it by this one, plus delta S of the system. But you know what? I don't want to have anything down here. So I can say, why don't I multiply everything by T? So if I multiply everything by T here, actually I will multiply everything by, if I multiply everything by T, I'm going to have T delta S univ is equal to delta H system, because this T is going to cancel with this T, but it's going to multiply here, it's going to multiply here, plus T delta S system. That's what I'm going to have. Then I'll say, let me multiply everything by -1. So multiply the whole bracket here by -1. I am going to have negative T delta S universe is equal to, the negative here will cancel with this negative. So this one will just be delta S delta H system. That is the enthalpy of the system. This negative multiplying by the positive, this part becomes negative. Minus T delta S system. So this is an important equation, and we will see why it is important. This part of the equation is another thermodynamic characteristic. So this part of a chemical equation, I will say delta T or T delta S universe is equal to delta G. This is called Gibbs free energy. So if I draw a line here, we can say that delta G is given by delta H system minus T delta S system. So normally we don't need to write system. We just say delta G is equal to delta H minus T delta S. Now this is the final equation that will tell us that this reaction is spontaneous or this reaction is non-spontaneous. So delta G gives us the change. So let me add here. It gives us the change in Gibbs free energy. That's what delta G is, because the delta stands for change. Now, once you get the delta G, you can be sure that you will know if this reaction is spontaneous or if the reaction is non-spontaneous. And in terms of a state property, if you are not dealing with change, you will say G is given by H and T S. Maybe let's talk about what is G. We say that G is just free energy. What is this free energy? This free energy is, we call it useful energy. It is a useful energy that a thermodynamic process can use, to do work. So how do we get the useful energy? We get useful energy by subtracting total energy minus non-useful energy. So this one can be your total energy. That is this part. This part is non-useful energy. So if you subtract non-useful energy from total energy, you get free energy. The energy that thermodynamic system is going to actually use. So we call that free energy. You are not going to use the enthalpy of the system, no, but you are going to use the free energy of the system, that is G. Now let's look at G again. We said delta G is equal to delta H minus T delta S. And we know that delta G is equal to minus T delta S of the universe. We know that. And we know from the second law of thermodynamics that entropy of the universe is greater than 0 in a spontaneous reaction. So if this part is greater than 0, it means the whole of this is going to be negative. If the delta S here of the universe is greater than 0, the whole of this is going to be negative. So, for a spontaneous reaction, delta G is negative. So I'll say for a spontaneous reaction, delta G is negative. That is the change in Gibbs free energy is negative. For a non-spontaneous reaction, delta G is positive. So the change in Gibbs free energy will be positive for a non-spontaneous reaction. A non-spontaneous reaction is a reaction that is not likely to occur on its own. Now, for an equilibrium reaction, delta G will be equal to 0. So for an equilibrium or reversible reaction, delta G is equal to 0. So those are the three situations of delta G. Let us look at the effects of delta H, delta S, and T on spontaneity of a chemical reaction. We are going to look at that based on this equation. The reaction will be spontaneous only when delta G is less than 0. So we need to take note of that. Reaction will be spontaneous only when delta G is less than 0. So if we have three cases. Case 1, if delta H is negative and delta H is positive. So I'm going to use numbers here. So let's say delta G, and I say delta H is maybe 20,000 joules, delta H, minus T, and delta S is 85 joules per Kelvin. But we say if delta H is negative, so I'm going to put negative here. So negative 20,000 joules minus T, 85 joules per Kelvin. So if this is negative, this part will be negative, and this part will also be negative. Which means the answer, which means delta G is going to be negative. So this means that at all temperatures, if you have a case 1 situation, the reaction is going to be spontaneous. So reaction spontaneous at all temperatures. So if you have negative delta H and positive delta S, the reaction is going to be spontaneous at all temperatures. Now, what about if you have positive delta H and negative delta S? So let's look at our numbers. So this time I have 20,000 joules for the delta H minus T, and then I have minus 85 joules per Kelvin for delta S. We will see that this will cancel with this one, and there will be a positive here instead of a negative. For this case, delta G is greater than 0. So here delta G is positive. This reaction is going to be non-spontaneous at all temperatures. Because it will always be positive. That's what it means. That is case 2. Case 2 where delta H is positive and delta S is negative. Let us look at case number 3. So let me use numbers again. Delta H in this case is positive. So we have delta G is equal to let's say still 20,000 joules minus, so we say delta H is positive and delta S is also positive. So I'll put 85 joules per Kelvin. What will delta G be? Now, if you raise this T, if you increase the temperature here of this one, there will be a time when when this part is 2000. The whole temperature times 85 is equal to 20,000, and the delta G will be 0. If you increase the temperature more, for this one, this part will surpass the 2000, and the delta G will be less than 0. So at high temperatures, this reaction will be spontaneous. At low temperatures, this reaction will be non-spontaneous. Because if you use maybe 80 Kelvin here, it will not be equal to 2000. You are going to have a positive G. But if you use, let's say maybe 500 Kelvin or 5000 Kelvin, the number here will be greater than the 20,000, and when you subtract, you have a negative G here. So this reaction is G is less than 0 at higher temperature. Delta G is greater than 0 at lower temperature. What does it mean? It means reaction is spontaneous only at lower temperature. Not only at high temperature. Reaction is spontaneous only at higher temperature. So if you have delta H positive and delta S positive, the reaction will be spontaneous only at high temperature and will be non-spontaneous at low temperature. So that's what this is telling us. If you have delta S, delta H, and delta S, you really need to study this one. If you have delta H negative, delta S positive, the reaction is spontaneous at both low temperature and high temperature. If you have delta H plus, delta H minus, the reaction is non-spontaneous at both low temperature and high temperature. If you have negative for both, the reaction will be spontaneous at low temperature, non-spontaneous at higher temperature. If you have positive for both, the reaction will be spontaneous at higher temperature and non-spontaneous at, the reaction will be, if you have both positives, the reaction will be non-spontaneous at low temperature and spontaneous at higher temperature. So study this table. It is an important table. Now let's talk about the third law of thermodynamics. The third law of thermodynamics says that entropy of a perfect crystal at absolute zero, that is 0 Kelvin, is equal to 0. So what it means, this information is important Because it tells us that we know that there is a certain point where entropy of a substance is zero. And that is given by the third law of thermodynamics, which says that entropy of a perfect crystal at absolute zero is equal to zero. So if you say that, let's say if I tell you that entropy of a certain gas is equal to 70 joules per Kelvin, I mean it. So entropies are absolute. Because we know they start from zero. They are absolute. That is not the case with enthalpy. Enthalpies or H are just relative. Because we don't know, we don't know the actual zero enthalpy. What we know is just enthalpy change. So you can know enthalpy change, but you cannot know the actual enthalpy because we don't have absolute zero enthalpy. While entropy, according to the third law of thermodynamics, the third law says that entropy of a perfect crystal at absolute zero is equal to zero, which means if we have 70, we know that, this 70 is starting from 0 to 70. Entropy, if you have 70, you are not sure. You are just saying, maybe this 70 we had two entropies. We had two enthalpies. We had an enthalpy that was at 170 and another enthalpy that was at 100. We subtracted them to get the change in enthalpy of 70. So that's why third law of thermodynamics is really important. So here we are going to again talk about relative entropies in different situations. Let us start with solid to gas. So entropy of solid. So entropy of solid less than entropy of liquid less than entropy of gas, especially when you are talking about same substance. We saw this for ice, water and vapor. But we can also talk about entropy in case of molar masses. I'll use the noble gases. Entropy of helium. So entropy of helium is less than entropy of neon. These are noble gases. We see neon has higher mass than helium. Less than entropy of argon. Less than entropy of krypton. And less than entropy of xenon. This implies the higher the mass, the higher the entropy of similar substances in similar state. All of these are in gas form. Entropy also will depend on the complexity of a substance. So, for example, argon, which is less complex, has lower entropy than nitrogen monoxide, which is more complex. So complexity will give you information about entropy. So nitrogen monoxide, which is less complex than nitrogen dioxide, which is less complex than dinitrogen tetraoxide. So dinitrogen tetraoxide has the highest entropy here because it is the most complex. In terms of solid versus aqueous solution, if we take sodium chloride solid, has less entropy than sodium chloride aqueous. So the aqueous solution of sodium chloride will have higher entropy than the sodium chloride itself in a solid form. So you need to study these about entropy. These relative standard entropies are very important. So that's where we end, and then we'll look at videos that will deal with how we solve problems in this case. Thank you.